So here, this initial density is close enough to 1 in this isentropic base of space, and the initial velocity is small in this anisotropic base of space with -1 plus 2 over p derivative for x1 and x2 variable, but for x3, it has 1 over p derivative. In this case, we can prove as long as this quantity is sufficiently small compared with this anisotropic norm of u0 small, u03, then we still have the global well-postedness to a 3D inhomogeneous Navier-Stokes system. So the novelty of this result is this isentropic structure of the density function is consistent with this anisotropic structure of the velocity field. So with this modulus condition, we can construct example as follows, which has large velocity field, but with very small density function, with very small density function. And here, all the result before requires derivative assumption for the initial density. We can even prove result without any derivative assumption, but still in the largest scaling invariant space, like mu 0 minus 1, LV infinity norm to be small, then we can still prove the global existence. But the main idea to prove the global existence of result like this is to use maximum regularity estimate for time involutionary Stokes operator. Because the initial velocity field belongs to this scaling invariant isentropic base of space. If you use this method, you cannot prove the convection velocity field belongs to L1 Lipschitz. So in order to prove the uniqueness, we do need this Lipschitz estimate for the convection velocity field. So to prove uniqueness, we do need a little bit more regularity for the initial velocity field. And this result can also be generalized by Hafele Dunshire and myself to the half space setting. The main difficulty of the half space setting is because of for the pressure term, there is no boundary condition. So the main work of this paper is to generalize the solution formula by Wukai for this homogeneous time evolutionary Stokes operator. So now let's introduce the notion of slew, what we mean slew variable. We denote this bracket of f epsilon xh x3 equals fxh epsilon x3. So here this xh equals x1 and x2. And this notion was first introduced by Jean-Yves Chemin and Isabelle Galguer to prove the global existence of large solutions to a 3D Navier-Stokes system. So what do we mean large, which means the initial velocity field is large in the biggest homogeneous space of space, b dot minus 1, infinity, infinity. And this slew variable initial data turns out to be useful to study the state of G, subset of G, of this H dot 1/2 Sobolev space. In fact, we can prove, joint work with Jean-Yves and Isabella, we can prove through each point of G passes an uncountable number of arbitrarily long segments which are still included in this G. And in fact, Jean-Yves and Isabella and Merspecco, they can prove the global well-postedness of the classical Navier-Stokes system with this called ill-prepared initial data, provided that this profile, W0, belongs to some Banach space, which is small, and which is analytic with the x3 variable. So now let's turn to our problem. The main talk of the main result of this talk is to study the global well-postedness of 3D inhomogeneous Navier-Stokes system with the initial density 0, epsilon a given by 0, epsilon eta, which equals 1 plus eta to the times the sigma 0 bracket of epsilon, and with initial velocity equals v0h epsilon 0. So here this epsilon and eta are positive real parameters, and this eta is independent of this parameter epsilon. For data like this, joint work with Yang, we can prove, giving initial profile sigma 0, V0h, which are functions and vector fields in the Schwarz class, and with a horizontal divergence of the velocity field equals 0. And moreover, for any z in R and j in 1, 2, the average of this sigma 0 times V0h equals 0. And moreover, we need this first momentum of this sigma 0, V0h, to be 0. With this condition, we can find two positive constants, eta 0 and sigma 0, such that for eta less than or equals to eta 0 and epsilon less than or equal to epsilon 0, this initial data given by 8 generates a unique global smooth solution to a 3D inhomogeneous Navier-Stokes system. So in fact, use the idea to propagate this isentropic norm for this transport equation and propagate this anisotropic norm for this velocity field, we can prove if this eta is less than or equals to epsilon to the power of sigma, with sigma greater than or equal to 1/4, we can prove the global robustness of this problem. And in fact, this result can be explained as ill-prepared initial data. According to the calculation by Yang and Isabella, this sigma 0 epsilon, bracket epsilon, of this homogeneous space of norm is lower bounded by epsilon to the power of -1/p. And also, this quantity is also lower bounded by epsilon to the -1/p. But all the well-posted results before require for p must be between 1 and 6 with this smallest condition with this velocity field to be small in this isentropic Bezoff space, with or without this smallest condition. But here, although the data is ill-prepared, we don't require any analytic assumption for the initial data. So now let's turn to the outline of the proof. The first step is the construction of the approximate solutions. The main idea, just as the classical Navier-Stokes system by Isabella and Yang, we are going to use 2D inhomogeneous Navier-Stokes solutions to approximate 3D inhomogeneous Navier-Stokes system. So just for simplicity, let's introduce this rendezvous equals rho minus 1. And A equals 1 over rho minus 1, which equals negative this rendezvous over 1 plus rendezvous. Then instead of this rho u pi equation, you can find another equivalent system of this A, U, and pi system. So here, let's denote this AH, VH, and pi h to be the solution to the 2D inhomogeneous Navier-Stokes system with a parameter z. Or equivalently, if we denote this rho h by 1 over 1 plus AH, this system can be equivalently reformulated as a system of rho h, VH, and pi h with the parameter z. So it's well known for 2D inhomogeneous Navier-Stokes system, as long as the initial density is away from 0, this system has a global existence has a global unique solution. So let's build this approximate solution. Let's denote this true solution by h epsilon, u epsilon, and pi delta epsilon, which equals the scaled function of AH, VH, pi of h, plus this remainder term. So if you substitute this formula to the classical 3D inhomogeneous Navier-Stokes system, you'll find this R bar epsilon should satisfy and formulate parabolic equation like this with the error term E bar of epsilon. So now let's take a look at this E bar epsilon. Because this AH, VH, pi h satisfies this 2D inhomogeneous Navier-Stokes system, this seemingly singular term disappear. And we have this following three terms. And in fact, it turns out only these terms, partial z pi h, makes trouble. So before we explain why it's trouble, let's recall the norm we are going to use in this context. In order to do this, let's recall the operators of localization in horizontal and vertical frequency. So delta kh means the frequency cutoff operator such that the horizontal frequency is around the length of 2 to the power of k. And similarly, we can also define this frequency cutoff operator, delta LV of k, such that the vertical frequency is around 2 to the power of L. And we also have this partial sum operator for this horizontal variable, when we also have this partial sum operator for the vertical variable. With this definition, we can define this anisotropic base of norm BSS prime of P by summation of KL 2 to the power of KS plus 2 to the LS prime times delta KH delta LV of AOP norm. So which means this function, if it's this norm to be bounded, it has S derivative for XH variable. XH denotes X1, X2, and for X3, it has derivative S prime. Because it's homogeneous, because this is a homogeneous dyadic operator, immediately it's easy to check this bracket of A epsilon in this anisotropic base of norm is equivalent to epsilon to the power of S prime minus 1 over P times this A of BSS prime norm. So in particular, it's easy to check this norm, like the indices S prime equals 1 over P, is invariant and the vertical dilation. It's easy to check by its definition. So let's look at all these terms in the error terms like F bracket of epsilon. Since there is no negative power of epsilon appears, the choice of the norm to the space like with last anisotropic base of norm with last indices 1 over P is mandatory. And then moreover, because of the transport equation, we need L1 estimate with time in Lipschitz space of the convection velocity field. We also need this L1 time integrability for this F. Then the scaling determines this index for the horizontal regularity, which is like L1T B minus 1 plus 2 over P, 1 over PP. So now let's look at this pressure term for the horizontal, for 2D inhomogeneous Navier-Stokes system. By taking 2D divergence to the horizontal divergence to the momentum equation of this 2D inhomogeneous Navier-Stokes system, you find this negative Laplacian H, pi H, equals divergence H of this term plus this term. So because of the divergence free condition of this VH, you will denote this round zero H equals zero H minus 1. Then we find this pi H can be splitted as pi LH plus pi QH, where pi LH equals negative Laplacian H inverse divergence H partial T 0 H VH, and the pi QH equals this. It turns out it's not so difficult to prove partial Z of partial QH belongs to this space L1 R plus B0 1 half. But the difficulty lies on this term. So here we can prove this term indeed belongs to this space, which means because of this operator, this tells you for the XH variable, partial T 0 H VH has to belong to B minus 1 to 1 base of norm, B minus 1 to 1 norm, B minus 1 to 1 norm in this space for the XH variable. So if this is correct, we need to prove this product partial t of rho h, v of h, should be belongs to this space of space, b minus 1, 2, 1, for the horizontal in two space dimension. But everybody knows for the product, the worst regularity is this product A times B. The worst regularity for the product in two space dimension should be R1 of R2. By embedding Bernstein inequality, this should be banded in two space dimension, like B dot minus 1 to infinity, instead of this B of dot minus 1 to 1. So in this way, it's impossible for us to have an estimate of this term belongs to this R1, R plus, B0, 1/2, 2. So in order to to bypass this difficulty, we introduce a correction term, W epsilon, pi 1 of epsilon. So here this Laplacian epsilon equals Laplacian h, which equals partial x1 square plus partial x2 square, plus epsilon square partial z square. Then because of this divergence-free condition, we need to put this epsilon square before this partial z of partial 1 epsilon. We introduce this correction term just to get rid of this bad term, partial z, partial L of h. So now let's introduce the following ansatz. A epsilon, u epsilon, pi epsilon delta equals the scaled function of A of h epsilon, u epsilon approximate, pi epsilon approximate, plus this remainder term. With this u epsilon approximate, pi epsilon approximate equals this scaled function of vh epsilon and pi h epsilon, plus this correction term epsilon, wh epsilon, epsilon, w3 epsilon. The reason why we scale like this is because of the divergence-free condition for the u epsilon approximate, and plus this epsilon, pi 1 epsilon of epsilon. So by substituting this formula to this classical 3D inhomogeneous Navier-Stokes system, you find this remainder term r epsilon gradient pi epsilon should satisfy a parabolic equation like this. Have a parabolic equation like this. With an error term, now E epsilon could be written E1 epsilon, E2 epsilon, and E3 epsilon plus this E4 epsilon. So next, let's turn to the estimate of all the error terms. So first, let's turn to the estimate of this E1 epsilon, which it can be written like this. So this estimate lies on the estimate of this VH and this correction term. Because here, this initial velocity, the initial density is not small in this isentropic base of space. All this estimate will depend on the decay estimate for the 2D inhomogeneous Navier-Stokes system. So now the main result is as follows. Let us consider smooth solution rho u gradient pi of 2D inhomogeneous Navier-Stokes system associated with initial data rho 0 u0, such that this capital U0 to be finite, and the average of the initial momentum equals 0, and the initial density to be close to 1. Then for any constant which can be explained as a scaling parameter of time, which has the same dimension as time, as this capital T is greater than or equals to this T0, rho 0 u0. We find the initial energy should decay like E0, that's initial energy, times T of T to the negative power 2. So this decay estimate is exactly as the optimal decay estimate for the 2D classical Navier-Stokes system. And with more derivative for the initial data, we can prove further decay estimate for the derivative. Like gradient of UTL2 should decay like T to the power of negative 3/2. And the partial T of U, second derivative of U gradient pi of UL2 norm decays like T to the power -2. And the gradient partial T of U L2 norm decays like t to the negative 5/2. But because of this transport equation, there is no decay for the density function. The third derivative of the velocity field does not decay like this, but it has to lose some decay, like logarithm of this bracket of t. So here we always denote this bracket of tau equals e plus tau. And ht of t equals ht over of this capital T. So the main idea of the proof, in fact, based on the method introduced by Wigner in 1987 for the classical Navier-Stokes system. So let's denote this g is a function defined on R plus with g squared grows like 3 times bracket of tau inverse. Then we define this low frequency set S of t, cosine belongs to S2 with absolute of cosine less than or equals to square root of t, square root of 2 over t times g of t of t. And we define this low frequency cutoff part, V flat of t equals this Fourier inverse of this restriction on the low frequency part of the Fourier transform of this V. So with this definition, we first have this energy estimate, which is standard. With this energy estimate, and also with this definition, we know this U flat should be perpendicular to this UT minus U flat in any Hilbert Sobolev space, in particular in H.1. Because of this orthogonality, we can split this gradient of U squared equals this part plus this part. But for this part, because of this definition, we have this part to be level bounded by 2 over t times g of t squared of t times u minus u flat L to norm squared. Then using, once again, this orthogonality of ut minus u flat of t and the u flat of t, we find this term equals this term. So now if we substitute all these two estimates to be here, we arrive at this differential inequality. So these terms on the left-hand side seems create the decay for rho ut L to norm. But this low frequency part seems prevent this decay for this square root of rho times u of t. So mainly, in order to get the optimal decay estimate, the main work lies on the estimate for the low frequency part. In order to do this, we introduce a completely new formulation for 2D inhomogeneous Navier-Stokes system. In the Fourier variable, we can write this as this. So here, this P here denotes the Lorentz projection operator. In this formulation, this pressure term does not appear. And here, this rho, let's round rho, equals rho minus 1. So eventually, because in L infinite norm, rho minus 1 is small, this term should be absorbed by the left-hand side. So in this way, as long as we have good estimate for this initial data, these two parts are good for this low frequency part. So because of this new formulation, we have exactly the same decay estimate for this low frequency part. That's the reason we can get exactly the same optimal decay estimate for the classical 2D Navier-Stokes system. And in fact, this decay estimate not only works for this V of H, the solution to 2D inhomogeneous Navier-Stokes system with a parameter Z. But also this decay estimate works similarly well for this derivative of partial ZH, T of dot of Z, and also second derivative partial ZZ, VH, V of T dot of Z. So with all the decay estimates, plus this interpolation inequality between this anisotropic Sobolev space, which means this function belongs to LP with vertical variable, LQ with horizontal variable, and a partial Z also belongs to this space. Horizontal gradient of this F also belongs to this space, and the gradient, horizontal gradient, times partial ZF also belongs to this space. Then we can prove this F belongs to this anisotropic Bezoff space. So with this decay estimate plus this interpolation inequality, we can prove this VH, partial ZVH, gradient VH, partial ZVH, partial Z pi H belongs to L2 in time or L1 in time to the values in the anisotropic Bezoff space. And also can prove this correction term, epsilon WH W3, also belongs to L4 in time, L2 in time, L2 in time, L1 in time, with values in this anisotropic Bezoff space. So with these two estimates, we can prove we can have a good estimate for this error term, E1 of epsilon. For instance, let's take a look at this term, just for example. For this term, because the last indices is 1/2, because of this homogeneity of this definition, as we explained before, this bracket of epsilon norm is equivalent to this part without this bracket. Then by applying this product laws in the anisotropic Bezoff space, we find that this product of this norm can be controlled by this norm times this norm. But we already have the estimate of this term and also this term, so we could have an estimate for this bracket. And all the other terms can be handled in the same way. So in this way, we can have a good estimate for the first error term. For the error term, E2 epsilon and E3 epsilon, which can be written explicitly like this, which equals main terms like A epsilon times F bracket of epsilon. So in order to estimate error term like this, we should have a good estimate for this A epsilon, which satisfies the transport equation. So in order to do this, we need the following induction assumption. Let P between 3 and 4, let's denote this T bar of epsilon equals the supremum for all T less than the lifespan of the solution, such that this L4 norm with respect to time T to this anisotropic Bezoff norm plus gradient R epsilon of L1 B or 2 over P with last derivative 1 over PP to be bounded by this R0. We should choose this constant R0 later. So with this inductive assumption, we can prove for this transport equation, we can propagate this anisotropic regularity. As we explained before, in general, it's not correct to propagate anisotropic regularity for the hyperbolic system. This problem is closely related to what's called propagation of conormal regularity to the classical hyperbolic system. But due to its spatial structure, here is initial data equals the bracket of A0 epsilon. We can still use this structure to propagate this anisotropic regularity. So proof turns out to be not so difficult in this case. We first scaled this function, this A delta epsilon, T of xh z equals A of txh z over epsilon. And we also rescale this convection velocity field in this way. Then you find this transport equation for this epsilon becomes this transport equation for A delta epsilon. And with initial data, there is no scaling. It's well known that for transport equation in the Lipschitz space, the Bezoff regularity of index less than 1 can be propagated. That's why for S between 0 and 1 minus 1 over P, this Bezoff regularity, B of S plus 1 over P, can propagate it by this L1 Lipschitz norm of the convection velocity field, which can be written in this way. Because of this spatial structure, we find that this gradient U delta epsilon, L infinity norm, can be controlled by the U epsilon we defined before. On the other hand, it was proved by Yang Yu and myself, this anisotropic norm can be controlled by this isentropic norm. And this isentropic norm by interpolation can be controlled by this subleft norm. And moreover, because of last indices is 1 over p, this anisotropic Bessel norm is equivalent to this A delta anisotropic Bessel norm. So in this way, we completed the proof of the proposition. So with this proposition applied to our system, we can prove with our inductive assumption for t less than or equal to t bar of epsilon. A epsilon of t, b of s1 over p, p with s between 0 and 1 minus 1 over p, this norm should be controlled by a constant which depends only on the initial data times eta times exponential times of c times r0. So now let's take a look at this e2 epsilon with a good estimate of this term plus the decay estimate of the second term by using the product laws in the anisotropic Bessel space. We can prove this e2 epsilon could be controlled by the right-hand side. And also, for the last term, for the E3 term, we have a similar estimate. Instead of this epsilon power here we have a small constant, C0 times eta here. So this completes the estimate up to E3 epsilon. So now let's turn to the most difficult term, E4 epsilon, which equals B epsilon times Laplacian h, VH, minus gradient h, pi h, bracket of epsilon. So the equation satisfy B epsilon should be like this. Partial t B epsilon plus U epsilon dot gradient B epsilon plus R epsilon dot gradient of AH epsilon plus epsilon W epsilon gradient of AH bracket of epsilon equals 0. So for this transport equation hyperbolic system, we split this B epsilon to be 3 parts. B1 epsilon, B2 epsilon, and B3 epsilon. For B1 epsilon, it satisfies transport equation with the source term within the power of epsilon. We also define B2 epsilon like this. Then because of this, the difference between U epsilon and a VH bracket of epsilon, we find another term, B3 epsilon, should satisfy an equation like this. So from these three equations, we find the first equation and the last equation, the source term always has a power of epsilon. And for the second equation, although it's a transport equation, there is no power on the right-hand side. But the observation here is that the convection velocity field only have convection in the xh variable for the x1 and x3, x2 variable. But we don't have this convection in the x3 variable. For a transport equation like this, we can prove the propagation of anisotropic regularity. And for this term and this term, we can use the classical LP type energy estimate. So in this way, we can prove the following proposition. For t less than or equals to this t by epsilon, we split this b epsilon equals this b by epsilon plus b delta epsilon, such that this anisotropic norm of b by epsilon is controlled by C0 eta times 1 plus R0 times t to the power of 1/2. And this b delta epsilon of t should be controlled by C0 epsilon to the power of 1 minus 1p times 1 plus r squared times t. So look at this estimate. That seems a disaster because we need a uniform estimate for the velocity field. But here, these norms of this b epsilon grows with respect to time t. So in this way, once again, we needed to use this decay estimate we obtained before for this inhomogeneous 2D inhomogeneous Navier-Stokes system with a parameter. By applying this interpolation inequality between subleft space, we can prove this decay estimate. We can transform the decay estimate of VH gradient pi h to be decay like this in the anisotropic Bessel space like t to the power of negative of 2 with this decay estimate. Then we can estimate this E for like epsilon, which equals B bar times Laplacian H, VH epsilon of this anisotropic base of norm. By product law, this in space variable, this product can be estimated by this norm times this norm. And this norm grows like square root of t. But here we have this decay, like t to the power of negative power of 2. So eventually, this decay will absorb this growth estimate of this time t. So eventually we can have this term should be controlled by C0 of eta times 1 plus R0. And similarly for this term, we cannot prove this space of norm decay estimate, but we can prove with this weight, this term should be bounded, bounded. So now we can estimate the last term, like B delta times bracket of Laplacian H, bracket of epsilon times this term of bracket epsilon. Firstly, by product laws, this inside term can be controlled by this term and this term. And this term grows like t, but this time t with this weight of this integral is finite. So eventually we still have this estimate. So this completes the estimate of all the error term. So last step is to estimate of the remainder term. This remainder term of R epsilon should satisfy an equation like this. Now we have a good estimate for this error term. We still need to estimate this pressure term. In order to estimate this pressure term, let's look at this elliptic system. Divergence 1 plus a gradient of pi minus f, this equals 0. This which can also be written in this way. So inverse of this Laplacian, you find this gradient of pi should satisfy an equation like this. By the famous Fourier Planck scale inequality, this MA of G L2 norm should be controlled by L infinity norm of A times G of L2 norm. So in this way, as long as this L infinity norm of A is less than 1, this gradient of pi equals this ID minus MA inverse times gradient Laplacian inverse of divergence F. So in this, in general, we can define this more general modified projection operator, Lorentz projection operator, by like P of A of F, which equals F of A minus this term. In the particular case, when this A equals 0, this operator is nothing but the classical Lorentz projection operator to the space of divergence-free vector field. So with the introduction of this modified Lorentz projection operator, we can rewrite our original system to the following way, like a partial T of R epsilon minus Laplacian R epsilon equals PA act on the right-hand side and the divergence-free condition on this R epsilon. So before we turn to the estimate, we needed some technical tools just to bypass the difficulty of Gromov type estimate. We introduce a G lambda weighted function of G lambda of t like this, G of t times exponential of negative lambda integral of 0 to t u, capital U epsilon approximate of t prime, dlt prime. With this capital U epsilon approximate of t equals the summation of all these four terms. So by multiplying, we formulate our system in the integral formulation and multiply G lambda t on both sides, we find R epsilon lambda should satisfy an equation like this. So now last step, we should estimate this integral formulation. So in order to do this, let's introduce the norm we are going to work. In this case, for p between 3 and 4 and t positive time, we denote this f of this fp of t, which equals this integral 0 to t e of t minus t prime Laplacian act on this ft prime dlt prime of this xt norm. And this xt norm equals L4 with respect to time to this space of space and L2 to this space of space. But partial 3 belongs to L4 over 3 and the gradient of f L1 to this space of space and the partial 3 squared f to this space of space. The reason why we cannot introduce here as a classical case like L infinity b minus 1 plus 2 over p, 1 over p of p. The reason is because the second derivative here have this estimate L1, b of 2 over p, p, 1 over p. But for the third derivative, we only have this L1, b to the minus 1 plus delta plus 3 over p, negative delta of p. So if we take L infinity, it's impossible for us to get an estimate for f in a space like f, L infinity of t in this space of space b of dot, b of minus 1 plus 2 over p, 1 over p of p. Because here we have a very bad estimate for the third derivative, for the second derivative, for the vertical variable. For this, we can, in fact, prove for p between 1 and infinity, alpha beta plus beta equals minus 3, minus 1 plus 3 over p, with alpha less than or equals to this constant and beta less than or equals to this constant. We can prove this FP norm should be controlled by this L1 from 0 to t, b of alpha beta, anisotropic base of norm. So with this estimate, we apply this estimate to the integral formulation we just obtained. We find this R epsilon lambda should satisfy an inequality like this. So now in this inequality, as long as here eta is sufficiently small and lambda is sufficiently small, these two terms will be absorbed by the left-hand side. And according to this inductive assumption, this term is bounded above by R0. So as long as this epsilon is sufficiently small, we find this term should also be absorbed by the left-hand side. So eventual estimate should be like this. R epsilon of x of t is controlled by 4c0 times exponential of lambda integral from 0 to t, this capital U epsilon approximate t prime d of t prime. And it turns out this U epsilon approximate of t of this norm is controlled by the right-hand side, by the summation of these two terms. And this norm is controlled by these two summation of these two norms. Then according to the estimate we obtained for this VH, and also for this correction term, we find this integral of this capital U epsilon approximate of t prime d of t is bounded by some uniform constant. So in this way, we have this R epsilon of x of t is controlled by this constant. So we denote this constant by C0 prime. So last step, as long as we choose R0 equals 2 of C0 prime, and the epsilon and the eta sufficiently small, like eta less than equals to this constant, and a C0 and the epsilon is sufficiently small, such that this 2 0 is bounded by the minimum of this constant. So eventually we can prove for t less than equals to this t bar epsilon, we have this R epsilon x of t should be less than equals to this R0 over 2. So in this way, by a continuous argument, we prove this t bar epsilon equals plus infinity. And the proof of the main theorem is complete. Thanks a lot for your attention.